Welcome to the third and final video of the week. In this video, we're going to expand our understanding of conversions between different units of measurement. In the past, we dealt with the moles and we dealt with the number of particles. We're going to incorporate mass and volume, or liters of gas, in this video. So technically, after the last video, this is where we were. We talked about what a mole was and how it related to number of particles. And if we're looking at it from a flowchart perspective, we have a relationship between particles and moles. And that relationship between particles and moles, or that conversion factor between particles and moles, is 6.02 times 10 to the 23rd. Well, there's a reason why we use the mole. The reason why we use the mole is particles are super inconvenient to measure by. No one wants to count exact number of atoms. No one wants to try to use numbers that are so astronomically big. So no one wants to be able to even consider counting numbers of particles. So we use the moles as clumps. But we have no way to actually physically measure a number of moles. We can calculate the number of moles, but we can't physically measure the number of moles. But what we can do is we can measure the mass. And where that's convenient is that if we want to look at mass and number of particles, we have the atomic mass in the periodic table. When we were talking about the periodic table before, we said that the atomic mass, the number on the periodic table, was the mass in atomic mass units of an atom. Well, we're halfway there. We're going to incorporate the mole now. And what's kind of cool is that mass on the periodic table, that number on the periodic table, the decimal number on the periodic table, is the mass of 1 mole of atoms in grams. So, for example, if I look at my periodic table that you guys all should have gotten when we did the other stuff, and actually let me reference this really quickly while doing all calculations associated with the Google Classroom or anything like that, please use the periodic table that I provided you, the blue one that I provided you. If you don't have a copy of that, I'm going to go ahead and put a copy on OneNote so that you can actually have that copy, but use that one because the numbers on that table are going to be the ones we're going to be using for all of our calculations. And today in our Flex Chat, we talked about the importance of getting the right numbers and the right sig figs. If you're not using the right numbers from a periodic table, you're just using something you found or back of a book or something, and they're off by a little bit, you're going to get frustrated with getting the wrong answers. So anyway, if I look at the spot for lithium on the periodic table that I provided with you, it has the number 6.941. What that means is if I had 1 mole, if I had 6.02 times 10 to the 23rd atoms of lithium, it would have a mass of 6.941 grams. Those numbers on the periodic table are conversion factors. They are relationships between mass, something we can measure, and moles, something we can count. There's also something called molecular mass, when that compound happens to be a molecule covalently bonded like water. If we just add up the masses, add up the atomic masses, we're going to get the molecular mass. Since there's 2 hydrogens, we're going to take 2 times the mass of hydrogen and add to it 1 times the mass of oxygen, and then add those together, do the sig fig magic. Notice that the first number has 5 digits past the decimal, the second number only has 4, so my final answer can only have 4 past the decimal. Sig figs really do matter. There's a lot of similar terms out there. They all kind of mean the same thing. Atomic mass, formula mass, molecular mass. Sometimes you're going to see, if you go on online and try to find explanations, they might use the word molecular weight, atomic weight. They all mean the same thing. They are the mass of the mole of whatever thing they're measuring. The mass of a mole, or whatever that substance is. They are all the same. They're the mass of a mole of whatever the substance is. If the substance is an atom, the atomic mass or atomic weight means the mass of a mole of that atom. Formula mass, molecular weight, they all mean the same thing. They are the mass of a mole of that substance. So what we're going to use is a generic concept called molar mass. Molar mass is just going to mean the mass of a mole of anything. And from my perspective, with me discussing it in terminology of a global explanation. If I'm talking about atoms, I say molar mass, you know you're talking about the mass of a mole of atoms. If I'm talking about molecules, you know that I'm talking about a mass of mole of molecules. We're going to use the same exact term, molar mass, to represent the conversion factor. It is a way to go between mass and moles. Let's see. So what we've added is another branch to our mole diagram. So if I need to go from mass to mole or mole to mass, I'm going to be using the molar mass of whatever substance I am going to be using. Okay, so let's see how this works. Suppose I want to try to use molar mass. Here's a question. How many moles are there in 19.5 grams of silicon? Well, silicon is an individual element. So much like all of our other dimensional analysis things, we're going to start by having our 19.5 grams. And then we're going to consider our conversion factors. Our two options, if you look at the silicon block on the periodic table, you see 28.0855. That means there's 28.0855 grams of silicon in a mole of silicon. So we're going to need to use one of these two conversion factors. Since we have grams, we want to use the one that has grams at the bottom so the grams can cancel. So we're going to use the second one. Grams cancel. Let me get my pen so I can cross it out. Grams cancel. I'm left with moles. So that means I get that the number of moles I have is 0.691. And that makes sense. I don't have quite a mole. A mole would be 28. I only have 19. So I have less than a mole. 0.69 is less than a mole. Try another one. Suppose I want to know the mass. Suppose I want to measure out 1.25 moles of oxygen. I want to be able to count the number of molecules using mass, but I don't want to go ahead and measure them. So first thing I need to do is start with my molar mass. Start with my molecules. And then notice that this is for O2. Oxygen gas is one of those diatomics. So 31.9988 is the number of grams. I want to use the one that allows me to cancel. So I'm going to use this one here. So when I cancel, now moles cancel, and I'm left with grams, and that means I have 40.03 sig figs, 40.0 grams of oxygen. That's a lot of oxygen. That's a lot of oxygen. What if I need to use molar mass and Avogadro's number? What if I want to go from mass, from atoms to mass? Atoms to mass. So I'm down here, I have the number of atoms, and I want the number of grams. There's no line that matches, there's no line here. There's no line here. So what I need to do is convert first to moles, then convert to mass. I need to do this in 2 steps. So let's see how that works. Particles to moles using Avogadro's number first, and moles to mass using molar mass. So particles to moles. So there are 6.02 times 10 to the 23rd atoms in a mole. I want to be able to cancel my units, so I'm going to use the second one. Atoms need to be able to cancel. And that has me at moles. And then I'm going to use my molar mass second. And I want to be able to get the moles on the bottom, so I'm going to use this one. Moles cancel. And when I do that, I get 333,000 grams of lead. That's a lot of lead. Another way. How many formula units are in 7.25 grams of sodium chloride? So now I have mass, and I want to go to moles. I have mass. I start here, and I want to get to particles. Well, there I'm just going backwards. I'm going to use molar mass first, and then I'm going to use Avogadro's number. Use molar mass first. There's my sodium chloride molar mass. And then I'm going to use the Avogadro's number. Again, making sure everything cancels out nicely. Okay, so we're able to go between mass, moles, mass, particles, all that fun stuff. Particles are not used very often. Used here mostly for to show how to use it. But honestly, no one wants to use particles. They're so small and the numbers are so big. Look at this. Look at this number of formula units we're dealing with. So what other options do we have? Sometimes mass is not convenient. Sometimes I can't weigh something. Sometimes I can't put something on a balance. When might I not be able to put something on a balance? Well, if you're paying attention to the objectives today, then you realize one of the places where you can't put something on a balance would be if it's a gas. So what we're going to do for Chem 1 and this stoichiometry unit is we're going to assume all gases are going to exist at what's called STP. And STP stands for standard temperature and pressure. Of course, gases will exist outside of 0 degrees Celsius in 1 atmosphere. Right now, wherever you're living right now, whatever room you're sitting in right now, listening to this video, very, very unlikely is the room going to be at 0 degrees Celsius in 1 atmosphere. Let's start by the fact 0 degrees Celsius is ding dang cold. Water freezes at 0 degrees Celsius, so that's crazy cold. And 1 atmosphere, it might be 1 atmosphere, close, not exact, but we're gonna focus on gases as they exist at 0 degrees Celsius in 1 atmosphere. It's a really, really good estimate for volumes and works pretty well. Come to Chem 2, and we're going to go ahead and discuss what to do when you're not at standard temperature pressure. So here's the deal. We're going to have what's called the molar volume of a gas. Molar volume, the volume of 1 mole. Any gas, as long as it's STP, and long as it's a gas at STP, will have the same exact volume. 22.4 decimeter cubed, or decimeter cubed is more commonly looked at as being a liter. So we have a conversion factor. We have 22.4 liters in a mole. 22.4 liters in a mole. So we have another conversion factor. How would we use it? Well, suppose I had a number of moles. I have 4.17 moles of gas, and I want to know what volume would that gas take up. So I start with what's given to me by 4.17 moles. Then I'm going to use my choice of 22.4 liters per mole or 22.4 liters per mole, getting my moles to cancel. So I got to use this one. So moles cancel. And when moles cancel, I do the math, 4.17 times 22.4, and I get 93.4 liters. What if I want to go the other way around? How many moles of nitrogen are in 35.9 liters? Okay, so I start with my liters. Again, I have my 2 conversion factors. This time I want to use this one because liters is in the bottom. Liters get to cancel. And I'm left with moles. Ta-da, 1.6 moles. Finally, we have the third installment of our mole diagram. We have mass, which is almost always easily measurable. Place something on a balance. We have volume, that's only for gases and only at STP. Only for gases and only at STP. And then we have the mole, that link between them. And particles is like we know they're connected to actual numbers of particles, but those numbers are astronomically huge. We won't use that a lot, but it's there. What if we had to use both molar mass and molar volume? What if we had to use both? It's like, for instance, if I want to know what is the mass of 6.89 liters of hydrogen gas? What's the mass of 6.89 liters of hydrogen gas? So they gave me liters, they want mass. They gave me liters, and they want mass. So I gotta go from volume to moles, moles to mass. So the first thing I'm going to use is 22.4, and then I'm going to use the molar mass. So I'm going to use my 22.4. Liters is on top, so I want the one with the liters on the bottom to allow my liters to cancel. And then I'm going to use my molar mass of hydrogen. I want to use the ones where the moles are in the bottom, so I can cancel it. Moles are in the bottom. And then I'm going to do the math. 0.620 grams is how many grams there are in 6.89 liters of hydrogen gas. Okay, so that wraps up this week's content for Chemistry 1 and all about the mole and different simple conversions. What's next? Next week, we're going to talk about percent composition, empirical formula, and molecular formula of a compound and how to calculate or determine the percent composition, the empirical formula, and the molecular formula of a compound. As always, stay safe, stay healthy, practice your social distancing. I hope to see you guys real soon. And thanks to last video, we now know that always remember, never forget, sig figs really do matter. You guys take care. I will see you on the next one. Toodles.